So particularly as chemists, AFM tends to be of greater use to us because we're not limited to conducting surfaces. We can look at polymers, ceramics, essentially anything that's not going to trickle out of the AFM cell, essentially. So say it's been with us since 1986. And we use, just to remind you from the previous lecture, we use some sort of mechanical deflection of the cantilever due to a force between a scanning tip and the surface. So the probe is very, very important, and the type of probe that you choose depends really on the sorts of information you want to get. And there's quite a host, and tips are almost always something you buy, except for very, very specialist applications where you might need to manufacture your own. Here's a few common examples. Particularly in the early days, the square pyramidal tip was very popular, made of silicon nitride. Probably most tips are now made of silicon. And the sharpness of the tip that we see will affect the quality or the resolution of the image that we can generate. And particularly if we have a surface with sort of mountains and valleys, something resembling the Alps at the nano level, then we need to be able to get into those valleys. And if we have a very, very blunt tip like the square pyramidal tip, then we're not going to be able to see the bottoms of the valleys. To be able to enter them, we need a very, very sharp tip with a high aspect ratio. And this can be taken to great lengths, and you can get by, for example, in the left-hand image, growing a diamond tip on the end of a conventional tip. You can get down to radii of curvature of the order of a nanometer, which give you a very, very sharp tip and which allow you to enter very, very small crevices on the surface. The bottom right image is a tungsten tip, almost the same sharpness. These are certainly not tips that we would use for conventional day-to-day imaging. They would typically be very, very expensive. Okay, so this sharp tip needs to be mounted on a spring because we're interested in the force. So from the deflection of the spring, we can extract the force. So typically we have two spring designs. The top right image, we see perhaps the traditional triangular shaped cantilever, which was thought to provide lateral stability. As we go into more dynamic aspects of AFM imaging, where we're oscillating the tip, we need to really understand the mechanics of the movement of the tip, and therefore the lower images, these sort of beam-shaped cantilevers, are increasingly replacing the triangular cantilevers. Typically, they're of the order of 200 micrometers long, 30 micrometers wide, and a couple of micrometers thick, perhaps. As the electronics and the measuring ability and the frequency at which we can record data increases, we're trying to go to higher and higher resonant frequencies of the cantilever, which means for modern systems, cantilevers are getting much shorter, and these would be considered ridiculously long in some of the modern dynamic AFM techniques. So let's just familiarize ourselves with exactly how we create the image. We have a so-called fast scan direction and a slow scan direction. So as we scan the tip over the surface, that's what we would call the fast scan direction. We would then step to the next line and either scan back or return to the beginning of the line and then scan that again. So those are essentially what give us our fast scan and slow scan directions. So our scanner is moving and following this sort of path over the surface, which is how we get the two-dimensional movement of the scanning. And I think it's important to note at an early stage that once we have an image, it's very easy to think of it as a photographic image, but it is a mechanical construction. It can be full of artifact and often picking what's artifact and what's real is one of the major challenges. So just to exemplify this at a trivial level, this is a polymer sample. It's exactly the same image, but you've just treated it in two different ways in the software. As you can see, you get a very different impression. On the left-hand image, the light color is associated with higher features, the darker is lower features. And the right-hand image, we've just essentially chosen to illuminate a topographic picture artificially, and the dark and light is shadow cast by the non-existent illumination of the surface. So whenever you look at an AFM image, there's an argument that says you should be suspicious and critical before you accept any information that it gives you. So there's a lot of advantages to using AFM. We get very, very high resolution typically. We get topography of the surface where we don't have to do any coating of the surface, like sometimes in SEM you need a gold coating, for example. We don't need that. We don't need in general to go to high vacuum. We can do it in ambient conditions. We can in fact locally heat or cool the sample so that we typically have a range from about -30 to about 100 degrees Celsius, which is pushing the limit, because then you have to start worrying about what's locally happening to the materials and the electronics. But in addition to topography, which is the first use of AFM, we can get a host of other properties such as frictional, adhesional, nanomechanical properties, and so on. And it doesn't take a long learning curve to come to terms with using an AFM. It's relatively easy and it's relatively inexpensive. Okay, there are, as with every technique, you have limitations. The dimensions that you can scan, if you want atomic resolution, typically you can only scan over nanometers. So you're really limiting the area you can look at any one time. You're limited by the material properties of the piezo scanner, how linear it is, by the resonant properties of the cantilever that you're using, and so on. And of course the fact that because we're looking at a mechanical construct, we can be looking at artifacts. So what's an AFM look like? This is an image from a company called NanoSurf. This is quite a small desktop AFM. You can see compared to a laptop computer, it's not very large at all. The smallest AFM, I think, can fit on the top, the fingertip. And this is an AFM completely engineered out of a single piece of silicon. In general, we don't need that sort of small scale, but it's pretty impressive that all the mechanical and piezoelectric control can be engineered into a silicon chip. They can also be very, very large. So this is a high vacuum AFM STM. In fact, one at Uppsala. We have similar equipment at KTH and the Kista campus. So AFM KTH has recently acquired something called the Center for Dynamic Nanotechnology, which is run by Professor David Haviland at Nanophysics, which has given us the opportunity to buy 4 new scanning probe microscopy platforms, which are located at the physics building at Albanova. It's got some unique imaging capabilities that really only exist here at KTH. We have strong links to 6 other AFMs on campus, and probably it's a reasonable bet that this is certainly one of the strongest instrument parks in the Nordic countries at any rate. So what we've recently acquired are the Bruker Icon Fast Scan and BioSPM, which allows essentially large images, large samples to be imaged. We're not limited by having to mount the sample on the scanner. We actually have the tip on the scanner, which means we can move over very large areas. It also has the capacity to image at very, very high speeds. We're not going to be discussing that, but when an AFM image typically takes of the order of a few minutes to generate, which to me, it still seems like a fairly quick image. When we can cut that down to seconds, obviously that makes your life as a researcher a lot easier. At the other end of the spectrum, we've got the capacity to look at biological samples, pretty much any way you want to. So with the instrument park we have, I think we have essentially the ability to look at the full gamut of materials. So let's start, based on historical reasons, I guess, with topographic imaging. So getting the three-dimensional structure of the surface. So to be able to do that, we actually have to understand the interaction of the tip as it approaches the scanning tip, the probe, as it approaches the surface. And what we do is we generate a force curve, a force versus distance curve, which looks like we see here. The negative axis refers to adhesion, and the positive axis is the repulsive part of the interaction. So the tip starts off at large separations, and as we come towards the surface, essentially van der Waals forces, if we're in air at any rate, lead to this attractive interaction. And then as we approach further, we make physical contact between the AFM tip and the surface. And we think of that as a hard wall physical contact where the electron shells are overlapping on the surfaces. So remember, repulsive is positive, attractive is negative. And we can image essentially using any part of the force curve that we want. In practice, we want a steep gradient to be able to improve resolution. So typically we'd be in the dark bars, the contact region, or the more steeply changing part of the attraction, which is a non-contact type of imaging. And of course we can, once we go into liquids, also have a repulsive force and be in a non-contact area. So contact mode has been around for a long time, since '86, and as you can see, so has this slide, but it illustrates the principles quite well. Here's our laser reflecting off the surface onto a photodiode, and that photodiode is detecting the movement of that AFM cantilever. As the piezo scanner under here moves the surfaces left and right, or backwards and forwards, depending which direction we're scanning, then this tip runs over the surface and in the same way as a record player, and gives us a picture of the surface. And there we're using then the deflection as our feedback signal. So we would try and keep the electronics would keep the deflection of the cantilever constant and move the surface up and down to keep that deflection constant. And from that movement we generate the topography. So here we can sort of see that as in a blow-by-blow approach. Here's the width of the cantilever and the sharp tip on the end here, and we try to have our beam deflected onto the center of the photodiode. So as we then scan across the surface, we can see the tip encounters this asperity or bump, and that shifts the laser on the photodiode. So then the software kicks in, and then an important factor here is the speed of the feedback loop, of course, and then the piezo, which in this case the sample is mounted on, will retract to allow the cantilever to return to its original deflection. Then as we go down the other side of the bump, we have the opposite thing happening, and then the piezoelectric crystal will expand again to restore the equilibrium position of the spot. Some people refer to this technique as repulsive mode, but the important thing to remember is that the AFM tip is making a continuous soft contact with the surface. Soft may not necessarily be that soft, in fact. And we can either keep the force constant or the height constant. 9 times out of 10 we keep the force constant. So just remember, because it's a spring, the deflection that we measure allows us to measure the force of interaction via Hooke's law, which is what we use for the constant deflection mode. In the constant height mode, remember, we're just scanning the surface. The tip is running over the asperities on the surface. If you bump into something which is the order of a few microns and have no feedback, then the chances are you're just going to snap off your tip. So height mode, or keeping the height constant, typically you would use for atomically smooth surfaces. So here you have an example of an atomic resolution obtained with contact mode AFM. This is a mica surface, which is essentially the smoothest material we have. It's atomically smooth. So we have a roughness over the surface of the order of angstroms. And you can see in the image that there's a nice, a noisy but a clear sort of hexagonal picture emerging, which is reflecting the mica oxide lattice. We might just take this opportunity to remind ourselves that it's a mechanical electronic image, and because of that we can do all sorts of filtering and manipulation, which sometimes is a good thing and other times may be unwise. But if we take a Fourier transform of the image that we just saw, which is what we see down on the bottom left, we can decide that the very high frequency part of the image is actually noise, which is a fairly good bet, since we're not expecting to see anything much smaller than atoms. And we can then artificially remove that noise signal and generate this much more convincing, if you like, an attractive image of the surface where the regularity becomes a lot more apparent. And then it's between you and your conscience how much you choose to manipulate the image in this way. Okay, another smooth surface which is relatively easy to get atomic resolution on is the graphene surface. So this is a 6 by 6 nanometer image of a graphite, a graphite surface. Where you can clearly see the lattice once again. So that was atomic scale, but the advantage of the AFM is that we can actually look at topography over a very, very large range of scale. So we can also look at micron or 10 micron sized asperities. So this is a 50 by 50 micron scan as opposed to 6 by 6 nanometers in the previous slide, where we can see different domains on, in this case, a metal surface, and we see very different heights. The height difference on this image is the order of a micrometer. On the previous image, it was the order of angstroms. Now, we talked about soft contact imaging before. The AFM can also be used in solution. The previous images were in either vacuum or air. But we can go into solution and we can actually image materials that are adsorbed on the surface. And once again, we need to understand the interaction of the tip with the surface to do this. So if you're, for example, putting a coating, a polymer or surfactant type coating on a surface, you can actually see this being done in situ in the liquid environment. So in this schematic, we see the sharp AFM tip approaching a surface which is coated with surfactant micelles, which in this case have an apparently spherical structure on the surface. And if we look at the image below here, we see the force distance profile. So at long separation, we get this fairly slowly decaying force, which reflects the double layer force between the tip and surface, essentially related to the fact that they both have a charge, which in this case is repulsive. As the tip comes into contact with the surfactant, we see this little wall, this steep region, and if we push even harder, we can actually push through that layer of adsorbed surfactant, and then we come into this hard contact corresponding to the layer below. And this sort of gives us a feel for the idea of the set point. The set point is the force that we choose to set between the tip and the surface to generate our image. So if we were to set a high set point, in this case, somewhere in this region, our tip would be going straight through the surface and we'd be getting a nice image of the surface underneath the adsorbed layer. We'd just be pushing the material away. If we get a nice little barrier like this corresponding to the adsorbed material, then we can choose to put our set point at a much lower force. And then we can actually sit on the adsorbed material and then scan over that without, hopefully, dislodging it. And we need a reasonably steep force because we need the situation where a large change in force corresponds to very small changes in height. Otherwise, we lose that resolution in the Z direction. So here we would have very poor resolution, for example. And here, this is just a very nice example from the literature where by tweaking the structure of the surfactant that's adsorbing to a mica surface, it's nice to have a flat surface to see the structures against. Very small changes in the surfactant structure lead to dramatically different aggregate structures on the surface. So we can see at one end of the spectrum, spherical aggregates as we illustrated in the previous slides. As the curvature of the aggregates changes, they form micelles, and eventually they form flat bilayer structures which are completely featureless and which are also typical of phospholipid type layers, so cell wall type lipids. So this was, particularly in the field of colloid science, this ability was an enormous breakthrough for colloid science. More recently, it's actually been possible to look not just at one layer of adsorbed material, but if we have a profile which has enough bumps in it, as in this case here where we have a couple of bumps, we can choose to sit and image at different distances from the surface. So this example is ionic liquids on now my memory fails me, I think a silica surface. And we have one type of structure very, very close to the surface where positive ions adsorb to the negative surface, which is driven by that ionic interaction. The structure of the subsequent layer out into solution or out into the liquid, it's an ionic liquid, is then not driven by Coulombic aggregation issues, but by more solvophobic types of effects. So we get a very different structure depending on how far we are away from the surface, and we can actually probe that surface with a tip in contact mode by just hovering essentially above the layer on the surface, up to several ionic layers away from the surface. So it's historically one of the most popular modes. It's still very, very useful, particularly in systems requiring atomic resolution. The disadvantage is because you're dragging this sharp tip over a surface that you might actually affect the surface itself. You may damage the surface, you may distort features and so on. Also, if you have the tip in contact with the surface for a long period of time, then you can get condensation of water if you're in ambient conditions around the hydrophilic tip as it makes contact with, for example, a hydrophilic surface. And that can also lead to artifacts that are difficult to understand and undesirable. So here's an example of a case where actually imaging the surface has changed the surface. So this is a cellulose film made by Langmuir-Blodgett deposition. It's a very, very nice, smooth model cellulose surface. And what we can see in the green square is the result of a previous image of the surface. So we've gone in, we've imaged inside the green square, then we've zoomed out a little bit and imaged a larger area. And you can see that where we performed the scan before, we've disrupted the surface. And we've actually got this corrugated pattern, which is reminiscent and basically related to the corrugation patterns that you get on dirt roads, which are heavily trafficked. It's essentially the same phenomenon. So we've disrupted the surface. We don't want to do that. We should maybe also point out that it can actually be an advantage to disrupt the surface. In the case of paint, for example, we can take our AFM tip and we can actually plow it through the surface deliberately, and we make you can see a deliberate scar on the surface. And from the properties of that scar, essentially by imaging the width and depth of the scar, we can extract information about the material properties of the material that we're looking at. So that is a legitimate form of materials characterization by deliberately damaging the surface. And of course there are also nano indentation devices which are related to AFM, which are purpose built for this very reason. This is an example of something called lithography, which is not really so much characterization, it's more interfacial design. So here you can see the logo of what was then the Institute for Surface Chemistry, YKI, which has been carved into a gold surface. So someone's actually done graffiti on a gold surface using an AFM tip. So that's a sort of a topographical lithography, if you like. And while we're on the subject, we can mention another important area that the AFM is used for. Again, not so much for materials characterization, but more for design. You can actually use the AFM tip as a pen. So you can either dip it in a chemical of choice and then use the contact between the tip and the surface to write a pattern on the surface using that chemical. And in this case, it's a thiol compound that's been used to write on gold. So it's a self-assembled monolayer. So in the early days, they used to dip the tip into the liquid of choice. More recently, people have actually designed AFM tips literally like fountain pens with a reservoir providing a constant flow of liquid to the tip as it draws on the surface. And of course, with CAD diagrams, you can essentially put any image you want on the computer and then make the AFM automatically generate that image on the surface. So this is typically used for nanopatterning, for example, in bioassay type applications, rather than just amusement. Okay, so we've talked about contact mode. If we want to avoid damaging the surface, then maybe we want to back off the surface and use non-contact mode. This had a sort of a big flurry of activity in the early 90s, but in the situation where you're in air, if you think back to that force curve, when you're off contact and it's a van der Waals force, which is determining the strength of that attractive interaction between the tip and the surface, that van der Waals force is very non-directional. It's not as simple as the outermost tip on the outermost atom on the tip interacting with the outermost atom on the surface. It's the sum of the interaction between all the atoms on the tip and the sum of a large number of atoms on the surface, which means that resolution goes down because that's a very large area you're sampling. However, if you actually go into liquid, where you're putting another material between the tip and surface, then this van der Waals interaction can essentially disappear or be very, very greatly reduced. And more recently, non-contact AFM has therefore had a bit of a revitalization, if you like, because once that limitation is removed, you can actually get very, very stable, high-resolution images with non-contact mode. So a few years ago, we were almost thinking of not bothering describing this technique. Now it's very much one of the powerful techniques again. So there's essentially two ways of going about it. It involves oscillating the tip in both cases. So essentially our AFM is artificially oscillated close to its resonant frequency, and we either follow the amplitude or the change in frequency as the cantilever approaches the surface. So of course it's out of contact, and as the cantilever vibrates down towards the surface, it picks up the interaction with the surface, gets very, very close before the interaction kicks in, and that modifies the amplitude and the frequency. So if we pin the amplitude to a certain value, force the feedback loop to maintain that, then we can sort of track the surface and get a good topographical image of the surface. The topography, getting a good topography image relies on the fact that wherever you are on the surface, the force-distance relationship is the same, which of course with a heterogeneous material is not strictly true. So in that case, we might actually also be sensitive to material properties. But obviously, and of course with the frequency modulation, the other thing we can do is just follow how the frequency changes as we approach the surface. And both these techniques are used. So here's an example of amplitude modulated non-contact imaging, which is fairly recent. This image was generated by Kislon Wojciechowski, who's now at EPFL, and who visited us in 2013. He's really pushing the amplitude modulation non-contact imaging to its limits. And what we're looking at here is actually images of ions close to a surface. And you can actually see the structure of the surface in liquid, and at points indicated by the arrows you can actually detect ions which are not bound to the surface but just loosely associated with it. And it's also possible to detect water structuring close to the surfaces as well. So this is obviously of importance for biological type applications, but it gives you a sense of the fact that non-contact imaging can actually be very high resolution. So one of the, I guess the real Trojans of the imaging portfolio is tapping mode or intermittent mode AFM. Once again, it relies on oscillation of the cantilever, but in this case, instead of just going into that long-range interaction between the surface, we actually go fully into contact with the surface and literally give it a little tap every time the cantilever swings down. Now, the amplitude of the oscillation is typically 20 to 100 nanometers. With shorter, more high-frequency AFMs, that number goes down dramatically. But historically, anyway, we're looking at those sorts of amplitudes. And we also need to be aware that, particularly for biological molecules, that we can be given that surface quite a slap. So you need to be a little bit careful what sort of set points, i.e. how hard you allow that tap to be. Now, the advantage of tapping mode is that there's very little lateral movement of the tip on the surface. The surface is being scanned laterally, the tip is going like this, so it only makes a very, very, very brief contact with the surface, and there's almost no dragging then of the tip on the surface. So this is very, very good for fragile or biological samples. Once again, small changes in amplitude are what we use to detect the position of the cantilever with respect to the surface, and thus allows our feedback loop to kick in. So typically what we'll do is set the set point just off resonance if we're looking at the amplitude, because here we've got quite a steep relationship between the amplitude and essentially how close we are to the surface. So the feedback loop can be very, very sensitive to small changes, and therefore we're sensitive to our tap depth. And the piezo will respond to keep the surfaces at essentially a constant separation. So we can see that schematically here. Imagine the blue tip resonating above the surface. What we're seeing here is its equilibrium position. As we meet an asperity, the amplitude will change because it's now starting to tap onto the surface. So what happens? The feedback kicks in. The piezo will then retract to restore the amplitude back to its original value. And we'll continue to scan until we get to the edge of the asperity, where suddenly our amplitude is now too far the other way. So the piezo will once again kick in to restore that set point amplitude. And from its movement, we sort of get an inverse image here of the surface, which we can then use to create an image of the surface. So the advantages of tapping mode are that we get high lateral resolution of the order of nanometers. We use smaller forces in general. We don't have this drag along the surface, and we tend to damage soft surfaces less. Tends to be slightly slower scan speed than contact imaging, but as our ability to drive AFMs faster and faster at much higher sampling frequencies increases, that limitation is certainly going away. Probably has gone away. There's a few more parameters determining the image quality, right? Because now we've got a dynamically oscillating AFM, so we're a little bit dependent on the properties, the material properties of the cantilever and its shape and so on. Really, for a contact image, all we're worried about is how sharp that tip is. In the early days, there were a lot of difficulties using tapping mode in liquid. That's getting increasingly easier as the technology improves. All right, so an example where we can have a material that is highly suited to tapping mode rather than contact mode is a paper coating. So a paper coating looks like these images, which are just different magnifications of the same surface. Most printing papers have a coating consisting of minerals, either clays or calcium carbonate or both. In this case, we can see the characteristic blocky, flaky structure there in the top right, top left, that is, image, which is typical of clay-like materials. And you can see at larger resolution, we just sort of see this granular structure. But because we have flakes that are essentially not always chemically bound to each other, just van der Waals forces, and because we have a lot of topography on the surface, particularly the topography is large of the same order as the length of our tip. So that leads to a bit of problems as we sort of start scraping material around. So if you try and do contact imaging on a paper coating, well, good luck to you. Tapping, on the other hand, where we're not dragging, allows us to get much better resolution. And just as we in passing, we can sort of see what the effect of a process called calendering is, which is a technique used in the paper industry. Essentially, it's like a mangle. You just run the paper through this nib, and it essentially crushes the coating onto the surface. So, and that's what allows you to have glossy or matte coatings, and you can actually see on the micron scale here the structure of a glossy and a matte surface. Obviously, glossy, you need to get a lot of light reflection, so you need to have a surface which is smooth, basically on the wavelength of light. Whereas for a matte finish, you want the surface to be rough on the wavelength of light scale. And you can see what we analyze from these images is a characteristic roughness parameter. This is the average roughness that's been used here, which is probably the least useful measurement, to be honest, of roughness. This and the RMS roughness are numbers which are often quoted for topography, and they often give no good description of the surface whatsoever, for reasons that we'll go into later. There's a whole catalogue of different roughness parameters, and the choice of roughness parameter that you quote should be determined by the nature of the roughness that you have on your surface and its scale. Okay, we can also use tapping to look at biological samples. So in this case, we're looking at small DNA fragments known as plasmids, which have been modified to provide an anchor binding point, which you can see indicated in these images by the brighter spots marked by arrows. And one of the reasons you want to modify bits of plasmid is maybe as means of sneaking molecules into a cell, for example, to provide therapeutic delivery to a cell. But you need to be able to see if you've modified your DNA fragment. If so, how does that affect the morphology of the material? By letting it stick to a smooth surface, you can then image it with AFM, and you can characterize the properties of that DNA. So these are very, very short fragments. DNA is usually much, much larger. And here we see examples of DNA string. These are much larger plasmids with a different application, which were imaged just a week or two ago by Ruben Alvarez Asensio at our labs. And here we can sort of see this spaghetti-like structure in some cases, and in other cases we get this sort of twisted structure, which we'll see blown up here. And what you can see, we're on the limit now of this intertangled structure. The strands of the DNA are wrapped around each other. What I did in this case was just blew up the image And as you can see, the pixelation of the image is just becoming apparent as a result. Clearly, if I want to study this strand, then what I need to do is shrink the size of my image and then increase the resolution, because I'm limited to a certain number of points on each scan as I scan along, pixels. So I want to constrain those pixels to a smaller area and gain resolution. While we've got this example of DNA, we'll think about an artifact of AFM, which is the tip convolution effect. So we have to come back to this thought that everything we see is the mechanical convolution of the tip surface interaction. So essentially the tip has to be sharper than the surface to get a decent image. And this slide sort of indicates those challenges. If we have a nice high aspect ratio tip here going over an asperity on the surface, we don't want the curvature of the tip to be determining the shape of the image. If, for example, we have this low aspect ratio pyramidal tip going over the same asperity, we're going to be contacting the tip at this point instead of at the end, and then we're going to be generating this observed structure, which does not reflect the surface topography. What is correct is the height, but the lateral dimensions in this case are completely skewed. So one of the ways that you check to see if you've got an imaging artifact, if you're a bit nervous about the shape of your tip, for example, you, instead of imaging in this direction, you can change to have the fast scan in the opposite direction, and then you just see, does the feature have the same shape irrespective of the direction that I'm imaging. So if you look carefully at those DNA images that we had before, you'll see that the apparent width of them is larger than a polymer chain should be. And that's for exactly this reason, that in fact the curvature of the tip is larger than the width of the chain. So as we image the chain, we get a broader image than is true. But the height of the chain is the correct height. So if you're trying to extract the thickness of a DNA chain out of an AFM image, it should be the height image that the height value that you use. So here's an example of an image generated by using a blunt tip. You might think that you've got a beautifully ordered surface, but if you look carefully, all those features are exactly the same size, have exactly the same orientation, and in fact the surface just consists of little asperities which are 30 to 40 nanometers long, and they're imaging the tip. So what those little triangular shapes are the shape of a blunted AFM probe. And here's just another image indicating that you might think that you have a beautifully aligned structure on the surface, maybe some sort of pneumatic phase. In fact, it's an imaging artifact. If you change the tip to an undistorted tip, that distortion might be because you've picked up material. That's one of the problems. You either get a chunk of contaminant on the tip, or you just wear down the tip by friction. You can see that the true structure of the surface is then revealed. So we can also get angstrom resolution in liquid. This is, to me, one of the most important developments, particularly for the biological aspects of AFM. This is an example from Susie Jarvis' research in Ireland. And she's got angstrom resolution in liquid on a phospholipid monolayer. So essentially the cell wall building blocks. And she's able to image both hydration layers, but also the structure corresponding to the different parts of the phospholipid molecules, and even pick up changes in height in the phospholipid monolayer corresponding to different chain lengths of the different phospholipids. From deconvoluting the frequency distance data that you see in the left image, it's possible to build a force distance relationship which you extract from the dynamic tapping signal. And there you can see that we get these oscillations in the force curve. These are a little bit related to the sorts of oscillations we saw with the ionic liquid before, but in this case we can actually see the size of these oscillations, which just at short range corresponds to the size of water molecules. So as the tip is coming in and imaging the surface, we're essentially displacing the water of hydration. And from this image you can actually determine how strongly the water molecules are bound to the phospholipids, and the degree and range of that hydration, which is incredibly important for biology. Right, so let's return to our image of the paper coating. On the left we see a topographic image, that characteristic blocky structure. On the right we see the same image, or an image of the same region, which is showing completely different properties. We've thrown away essentially the topographic information, and we're looking at material properties of the surface. So in the next set of lectures we're going to be examining ways of studying more material and chemical properties of the surfaces.